This is our A2Further. We're in chapter 5 and we're taking a wee look then at series and expansion in the Maclaurin series. So as a wee reminder of stuff then from our A2 regular maths, we can find the summation of a series using these formulas here. And of infinite series as well, we have the sum to infinity is 1 over 1 minus x. Maclaurin effectively reverses the question. It asks us then, if we just change this round, we're now going to reverse the question asked above and asked whether, if given a particular function f of x, we can discover a convergent power series of which is the sum. We need to be able to differentiate it any number of times, and if we start to work our way through this, then we can use this formula here and then work it out. So the good news is the Maclaurin formula is given in the formula sheet, and so you'll see this then on the formula sheet, but it's best explained by actually running through a few examples and then working out from there. So obviously we let f of x equal our e to the x here, and we want to find all this information here out. So we want to find out then f of 0. So if we put 0 into here, anything to the power of 0 gives us 1. So that then would be 1. We want then f dash of 0, f double dash of 0, and so on. So if we differentiate e to the x, we of course get e to the x, and then dash 0 is just going to be 1. And there's not much happening in this particular example because it just always stays the same. So differentiate this again. This is a third. This is d3y by dx cubed, which again gives us e to the x. And we'll do one more. That just gives us 1. So then by the Maclaurin series, and again looking up there, if we sub in all our values, e to the x is going to equal, so let's again look at this, see if we can fit everything into one screen, actually would be helpful. F of 0, which is 1, plus 1x plus 1x squared over 2 factorial plus x cubed over 3 factorial, and then plus, hopefully you can see the general form here, first term, second term, third term, with x to the r over r factorial. And this one is valid then for all values of x. Let's take a look then at our next example, which should hopefully shed a little bit more light on the way we work this out. So cos x, again start off with, get this straightened up very slightly so we can get a bit of a clearer picture. So we're going to differentiate this a load of times. So if we differentiate cos x, we get minus sin x. If we differentiate minus sin x, we get minus cos x. If we differentiate minus cos x, we get sin x, and if we differentiate sin x, we get cos x. What we need from this then is f of 0. If we put 0 in for here, cos of 0 is of course 1. Sin of 0 is 0. Cos minus cos of 0 gives us minus 1. Sin of 0 gives us 0. And then we're kind of back to the start again with cos. This starts to repeat itself obviously after 4. If we're back to this and we differentiate again, then we get minus sin and minus cos and so on. So then our Maclaurin expansion, then we have cos x is equal to 1 And then the next term actually disappears, so our x term disappears, and then our next squared term then is going to be negative. So it's x squared over 2 factorial. The next term disappears, which is our cube term, and then our fourth term, x to 4 over 4 factorial. And then our general term for this is minus 1 to the r. That's our way of rotating whether it's going to be a positive or a negative. X to the 2r, because we're going to multiples of 2, and then 2r factorial goes on. And again, like the previous one, is valid for all values of x. Let's try our next one. So ln 1 plus x is our function. And let's see what we're going to have for this. Let's start to differentiate it. F dash of x is going to be 1 over 1 plus x. I hope we're okay with that. Differentiate the bottom, you get the top. So it's like our ln function. I'm going to write that actually as 1 plus x to the minus 1. It's just easier than to differentiate it next time. Double dash of x. So differentiating this, I'm bringing this minus 1 to the front. And subtract 1 from the power is minus 2. Minus 2 times the minus 1 then gives me a positive 2. 1 plus x to the power of minus 3. And then our fourth power, minus 3 times 2 gives me minus 6 upon 1 plus x to the power of minus 4. Now this is only ever used for our f of 0, so let's see what it gives us. F of 0, if I put 0 in here, ln 1 is of course 0. If I have 0 here, we're going to have 1 to the power of minus 1, which is 1. 0 here, so 1 to the power of minus 2, that's just 1, and then it's a minus. So we have a minus 1 here. 0 here, so it's a 1 times a 2. And then we're going to have a minus 6. If we were to sit and multiply this next one, then it'll be 24. I'm not sure if you recognize those numbers, 2, 6, 24. Those are the factorial numbers as you multiply up. So it's going to make our life then a little bit easier. So then by Maclaurin expansion, then ln 1 plus x is going to equal, first one 0, so that 1 doesn't appear. Then we're going to have x minus x squared over 2 factorial plus 2 factorial, which is our, I guess, different way of writing it, x cubed over 3 factorial plus 3 factorial x to the power of 4 all over 4 factorial. And see if I can just about squeeze this in here. There's a wee bit of writing involved. Minus 1 and to the r plus 1, r minus 1 factorial x to the r all over r factorial. This will of course tidy up. Gives us then x minus x squared. 2 factorial is just 2. If you have 2 factorial divided by 3 factorial, it just gives you 3. I hope we're okay with that. So that's 1 times 2, that's 1 times 2 times 3. So the 1 times 2's cancel out and you're just left with the 3. So it ends up giving you x cubed over 3. So it's much tidier. Again, 3 factorial cancels here, just leave me a 4 in the bottom. So it's x to the power of 4 over 4 plus, and again we can get our tidier version of this. Thank goodness, minus 1 to the r plus 1, x to the r over r. The validity of this then does change very slightly. And this expansion is valid between minus 1 and 1, minus 1 are equal to 1. Okay. If we could quickly go on to our last one, which is actually a little bit more straightforward. So hopefully we'll be okay with this. Right. Work out what's doing. There we go. So it's sine x, very like the cos x one. F of x is sine x. I differentiate that. I get cos x. Differentiate again. I get minus sine x. Differentiate again. Differentiate minus sine. You're going to get minus cos. Differentiate minus cos. You're going to get sine x, and that's us kind of back into the cycle. Those cycle 4 kind of keep appearing again. F of 0 is 0, dash of 0. So if I put in 0 here for cos, I of course get 1. 0 minus 1, and then this would be 0 again. So then by the Maclaurin series, sine x equals x, because our first term disappears, so this is our second term, so the 1 disappears, we have x, and the x squared term disappears, so it's x cubed over 3 factorial, x to 5 over 5 factorial, and so on. And our formula for that is minus 1 to the r plus 1, x to 2r minus 1 all over 2r minus 1 factorial.